Ryan. Ryan.
Solid, guys. We'll just keep that.
Ryan. This is how this song goes. This is stupid.
Ryan.
Look how this is all going on in the video. Ryan. This is stupid.
Ryan Seaback.
Angle of reflection is equal to the angle of incidence relative to the normal line of the surface.
So this ball is going to be a ray of light. Flex off. The same angle it went at. All right. So here is our reflective surface. Let's put in our normal line perpendicular to that. All right. Now here is our incident ray of light with our angle of incidence right here. That is going to be equal to the angle of reflection. Theta 1 equals theta 2. As you can see, this is what happens when
Are you recording this?
Maybe.
Oh my god. Okay, so when Ryan Seaback over here shoots a spray bottle, not into my eye, but actually on the laser, you can see it for some reason. He keeps on spraying it. My hand's wet now. Okay,
Is
keep
it
spraying
moist
it.
yet?
Okay, yeah. So when you spray it, you can see the laser, and at the same time, what's it called? There's a mirror here. I don't know if you could tell or not. There's a mirror there, and as the laser approaches the mirror, it reflects off it at the same angle it approached it at. So since the mirror's at an angle, it leaves it at the same angle. Also, there's a laser there. Didn't know if you could tell because Ryan keeps on spraying it like no one knows. All right, Austin, say something. The project requires you to say something.
Basically, in simpler form, what Parks is saying is the angle of reflection is the same as the angle of inflection.
No, incidence.
Incidence. Yeah. Yeah, that word right there. That's what I'm struggling with.
All right.
Today.
All right. So, because light travels at different speeds through different mediums, we get what's called refraction. That's like when a straw looks like it's bent or broken in water. So, a common way to signify this is through Snell's law, which is n sub 1 times sine of theta sub 1 equals n sub 2 sine of theta sub 2. N sub 1 is going to be the refractive index of the first, the initial substance that the light is going through. Then n sub 2 is of the second substance, and I've got over here a couple common refractive indices. A vacuum, by definition, is 1. So, yeah. So, a common way to demonstrate refraction is by explaining it like as in a wheelbarrow being pushed from pavement into grass. It's going to go slower in the grass than it does on the pavement, much like light goes slower in certain mediums than it does in others. So, Jared here is going to be my wheelbarrow. Would you mind? Alright, so I'm going to push him on the pavement in a straight line. This way. Now forward. Mush, mush, mush. So now he hits that, and then he slows down and goes at a less steep of an angle. Much like that. Snell's law! Snell's law! Good?
Yep.
Gucci? Okay. So, ray diagrams of thin lenses. This is going to be a convex lens with the object behind the focal point. So what you see is we've got 3 lines that you're going to draw to produce your image. So you're going to draw your line from the top of the image parallel to this principal axis that goes right through the center. You're going to draw a line that goes right through the center of the lens. And then you're also going to draw a line that goes down through the focus to the lens and then parallel to the other side of the principal axis. So where those intersect is going to be your image. And since this image is inverted, that means that it is a real image. If it were right side up, it would be a virtual image. So here, let's go over another example with a convex lens. Again, where we've got the object this time. Let's put that in front of the focus. So here's our first focus. Here's our second focus. So first, let's draw the one parallel. So that goes parallel, and then that drops down and intersects with the opposite focus. Then we're going to draw one through the center, like that, and then one that. Where does this one go? This one is going to go this way, actually. It intersects with the focus, and then it's up here. So see how these never actually intersect? So what you're going to do is you're going to then trace them back. Right here is where your image is produced, behind the object actually. So here's the image, and since it's right side up, and that means that it's going to be a virtual image. All right. So concave lenses are going to behave differently than a convex lens. We're still going to draw those first primary rays. So let's draw one parallel to the principal axis. Then this one, because of the nature of a concave lens, is actually going to go upwards, and it's actually going to be like this. So it's going to follow a line like that. And then let's get one that is, this next one is, this one goes to this other focus over here. So let's just draw that like that. Oops. Close enough. So then these ones are going to go out parallel to the translational axis, or principal axis. And then again with the one through the center, just like that. So now we're going to look at this way. We're going to bring, we've got this one here, this line here. This one here is going to come back here. This is where they all intersect. Right? 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 Yes, that's where they all intersect. This is where our image is produced. Again, since it's right side up, it's not inverted. That means it's a virtual image again. And yeah, there you have it. Ray diagrams. Ray diagrams of thin lenses. Okay.
Your parsa is sagi bayat.
There's a thing over here. You can look at it. Don't point anything in my face.
Alright, so now we're going to talk about what all this stuff Dr. Ryan Seebeck actually means.
Not a doctor.
Anyway, when a laser is fired into this rectangular prism, it is refracted by the change in the value of n between the air and the glass. That causes the laser to be refracted at a different angle when it goes to the other side of the prism. When it exits the prism, however, it is refracted at the same rate it was refracted by the prism. Therefore, the laser that is fired into the prism and that come out are parallel to each other.
Neat. Solid. Science. Okay. Review. We've got Snell's law. N1 of sine of theta.
Excuse me?
Oh, what?
You're going to have to come with me.
I have to come with you.
With me, hands behind your back.
What the Schnell?
What the Schnell is going on?
I'm looking through John's lunch.
It's my lunch.
What's he in there rest for?
Making the worst science video of all time.
Or math.
Probably.
Probably meth.
Turn it off.
Turn off. Closing time. We need 10 minutes on this video, so we're stalling for time. Yeah, I rhyme time with time.
We need 10 minutes.
That's not the lyrics.
Only 9.
It's improv.
So we're just making up some stuff.
I know that you all want us to go. I know that we want to end the show. I don't know.
We have 30 seconds. It's good. Whatever.
That it right.
Take it away, Austin.
Closing time.
That's not the lyrics.
Let's just end this.